quantum mechanics offers a world that feels vastly different from what we encounter in everyday life, challenging our sense of order and predictability. Unlike classical physics, which thrives on definitive outcomes and measurable certainties, quantum mechanics operates on probabilities, uncertainties, and strange principles. At its core lies the uncertainty principle, which declares it impossible to simultaneously determine the exact position and momentum of any particle. This is not due to any fault in technology or observation, but rather an inherent property of nature itself. The principle, introduced by Werner Heisenberg, states that the more precisely we know a particle's position, the less we can determine its momentum, and vice versa. This peculiar truth reshapes our understanding of how particles move and interact, forcing us to accept a reality where predictability is limited and randomness plays an intrinsic role. The implications extend far beyond simple measurements, giving rise to concepts like zero-point energy, a minimal energy that remains in every system even at its lowest temperature. Zero-point energy is an unavoidable consequence of quantum mechanics, and it persists even when all observable energy seems to have been removed. In a classical sense, cooling a system should bring particles to a complete halt, yet quantum mechanics forbids this. The energy tied to quantum motion cannot be entirely eliminated. Particles, even in their quietest states, are in constant, jittery motion. This restless behavior originates from the fundamental uncertainty in knowing both a particle's position and its momentum. These movements, often described as quantum jitters, are a reflection of the deep, ever-present activity within the quantum world. The energy associated with these fluctuations is not merely theoretical but measurable, influencing the behavior of systems in profound ways. For instance, it explains why certain physical properties, such as the resistance of materials at extremely low temperatures, behave differently than predicted by classical physics. The jittery behavior of particles is not confined to matter alone. It extends to empty space itself. What we perceive as a vacuum is, in reality, a dynamic stage teeming with quantum activity. The classical notion of a vacuum as completely empty space is replaced in quantum mechanics by a vibrant field filled with fleeting particles and energy. This quantum vacuum is a realm of constant fluctuation where virtual particles appear and vanish in pairs. These particles borrow energy from the vacuum for the briefest moments before disappearing, leaving subtle yet measurable effects. One example of this phenomenon is the Casimir effect, where two closely placed metal plates in a vacuum experience a small but observable attractive force. This force arises from the interplay of quantum fluctuations between the plates, showcasing how even the emptiest spaces are rich with hidden forces and activity. This concept of vacuum energy, a direct result of quantum fluctuations, is further explained by quantum field theory. Unlike the classical view that treats fields as smooth and continuous, quantum field theory reveals that fields themselves are inherently restless and jittery. At every point in space, these fields fluctuate, giving rise to particles as disturbances or excitations within them. The vacuum, in this framework, is not a state of nothingness, but a field brimming with latent energy. This vacuum energy is not confined to a single location, but spreads across space, influencing the behavior of particles and forces on both microscopic and cosmic scales. Its effects are not limited to the quantum realm, but ripple outward, shaping the structure of the universe itself. The vacuum's restless energy is believed to contribute to the accelerated expansion of the universe, a phenomenon attributed to the mysterious force of dark energy. The role of the uncertainty principle in defining this jittery reality cannot be overstated. This principle does more than set limits on how precisely we can measure certain properties. It dictates the very nature of quantum systems. It explains why particles can exist in multiple states simultaneously, creating phenomena such as superposition and entanglement. Superposition allows particles to be in different places or have different energies at the same time until measured, while entanglement links particles in such a way that the state of one instantly influences the other, regardless of distance. These phenomena defy classical intuition and underscore the probabilistic nature of quantum mechanics, where reality itself appears to be a collection of potential outcomes rather than definitive states. The quantum vacuum, governed by these principles, serves as a vivid illustration of how the uncertainty principle shapes reality. Because quantum fields must obey this principle, they can never remain perfectly still. Even in the absence of particles, the vacuum is alive with fluctuating fields that create energy out of apparent nothingness. This energy, though imperceptible in daily life, has profound implications. It underpins the stability of atoms and the formation of forces that govern the universe. Without the jittery foundation provided by the quantum vacuum, the universe as we know it would not exist. This restless activity connects the smallest particles to the largest cosmic structures, creating a seamless tapestry of interwoven forces and energies. While the vacuum's jittery fluctuations seem abstract, they manifest in tangible ways. Consider the Lamb shift, a small change in the energy levels of hydrogen atoms caused by interactions with vacuum fluctuations. This phenomenon provides direct evidence of how the vacuum's restless nature affects physical systems. Similarly, the quantum vacuum is critical in explaining phenomena such as the spontaneous emission of light from excited atoms and the stability of molecular bonds. These effects demonstrate that quantum mechanics is not confined to theoretical constructs, but has a direct and measurable impact on the physical world. The concept of vacuum energy also raises profound questions about the nature of reality. If empty space is not truly empty, but filled with fluctuating energy, what does this reveal about the universe's origins and ultimate fate? Quantum field theory suggests that the vacuum's energy is not a static property, but one that evolves over time, influenced by the expansion of the universe and the dynamics of quantum fields. This perspective ties the smallest scales of quantum mechanics to the grandest questions of cosmology, bridging the gap between the micro and the macro. The jittery behavior of quantum fields also highlights the interconnectedness of all things. At every point in space, these fields are active, shaping the properties of particles and forces. This interconnectedness is a hallmark of quantum mechanics, where no system exists in isolation. The behavior of particles is influenced by fields that span the universe, and the vacuum itself is a dynamic, ever-changing entity. This perspective challenges classical notions of separateness and locality, replacing them with a vision of reality as deeply interconnected and interdependent. Through the lens of quantum mechanics, the universe appears as a restless and dynamic place, governed by principles that defy classical intuition. The uncertainty principle, zero-point energy, and the jittery quantum vacuum all point to a reality where certainty is replaced by probabilities and where even the emptiest spaces are alive with activity. This view not only reshapes our understanding of the physical world, but also offers a glimpse into the profound and mysterious forces that drive the cosmos. Quantum mechanics does not provide all the answers, but opens the door to a deeper understanding of the universe's intricate and restless nature. The quantum vacuum, teeming with activity, stands as one of the most fascinating aspects of modern physics. Far from being a mere theoretical construct, The vacuum exerts influence on the physical world in ways that demand attention. These influences are rooted in the incessant fluctuations governed by the principles of quantum mechanics. Virtual particles, which briefly materialize and vanish, are not limited to esoteric phenomena, but contribute to observable effects. One striking example is the influence these fluctuations have on atomic stability. The electrons orbiting an atomic nucleus are not static. Their behavior is deeply shaped by the jittery fields that permeate even the emptiest spaces. This interplay between particles and the vacuum fields ensures that atoms maintain their integrity, allowing matter as we know it to exist. The interplay of vacuum energy and quantum mechanics also offers a deeper understanding of forces that operate on cosmic scales. In the context of general relativity, the vacuum's energy density contributes to the overall curvature of spacetime, which governs gravitational interactions. This connection between the microscopic quantum world and the macroscopic cosmos challenges the boundaries of classical physics, illustrating the profound influence of quantum fluctuations. Theoretical models suggest that the same jittery vacuum fields responsible for the behavior of subatomic particles might also play a role in shaping the evolution of galaxies and the large-scale structure of the universe. These insights bridge the gap between the very small and the incomprehensibly vast, offering a unified vision of how the universe operates. The uncertainty principle lies at the heart of these connections, shaping the behavior of quantum systems at every level. It not only governs the properties of particles, but also dictates the fluctuations of fields that fill the vacuum. By enforcing a minimum level of activity, even in the absence of particles, the principle ensures that the vacuum remains a source of dynamic energy. This dynamic nature is reflected in phenomena such as the spontaneous emission of light from atoms, where energy fluctuations cause excited electrons to release photons and transition to lower energy states. Such processes are fundamental to the behavior of matter and underpin technologies ranging from lasers to quantum computing. The jittery activity of the quantum vacuum also sheds light on the origin of certain universal constants. Parameters such as the strength of fundamental forces or the masses of elementary particles are not fixed arbitrarily, but arise from the complex interactions within quantum fields. These constants define the behavior of matter and energy, setting the stage for everything from chemical reactions to the formation of stars. Without the underlying fluctuations in the vacuum, these constants might take on values that render the universe unrecognizable. This connection between quantum mechanics and the fundamental properties of nature reveals a deep interdependence, where the smallest scales influence the largest phenomena. While the vacuum is often described as empty, this description masks its true complexity. At the quantum level, what appears as emptiness is a seething arena of possibilities. Virtual particles constantly emerge and interact, only to vanish again, contributing to a constant background of energy. This vacuum energy, while subtle, is anything but negligible. It has profound implications for our understanding of the universe's fate, influencing phenomena such as cosmic expansion. Observations suggest that the vacuum's energy might be driving the accelerated expansion of space, a mysterious phenomenon often attributed to dark energy. If this connection holds, it would mean that the jittery vacuum not only shapes the quantum world, but also determines the trajectory of the cosmos. Quantum field theory provides the mathematical framework to understand these dynamics, extending the principles of quantum mechanics to encompass the fields that permeate space. Unlike classical fields, which are smooth and continuous, quantum fields are inherently discrete and fluctuating. These fluctuations are not random noise, but are governed by the precise rules of quantum mechanics. At every point in space, these fields ripple with energy, creating particles as disturbances within them. This view replaces the classical notion of particles as independent entities, with a perspective where particles are manifestations of the underlying field. This paradigm shift transforms our understanding of matter, energy, and the forces that govern them, offering a coherent framework that unites the seemingly separate realms of particles and fields. The quantum vacuum also plays a pivotal role in the emergence of forces that operate at both microscopic and macroscopic scales. Electromagnetic forces, for example, arise from the interactions of charged particles with the quantum fields that surround them. These fields are not static, but vibrate with the restless energy of the vacuum, creating a dynamic backdrop for the interactions of particles. The same principles apply to the strong and weak nuclear forces, which govern the behavior of atomic nuclei. Even gravity, traditionally viewed through the lens of classical relativity, is now understood to interact with the quantum vacuum. These connections illustrate how the fundamental forces of nature are deeply intertwined with the jittery, fluctuating fabric of space itself. One of the most striking consequences of vacuum energy is its role in the phenomenon of spontaneous symmetry breaking. In the early universe, as temperatures cooled and quantum fields evolved, certain symmetries that once governed the behavior of particles and forces were broken. This process, driven by the dynamics of the vacuum, gave rise to the distinct forces and particles that populate the universe today. Without these symmetry-breaking events, the universe might have remained a featureless expanse, devoid of the complexity needed for stars, planets, and life. The jittery vacuum, with its constant activity, thus plays a crucial role in shaping the universe's structure and diversity. The role of the uncertainty principle in these processes cannot be understated. By enforcing limits on what can be known and measured, it ensures that the quantum world remains a dynamic and interconnected system. This principle is not merely a restriction, but a source of creativity, enabling the phenomena that make the quantum realm so unique. It underlies the dual nature of particles and waves, the probabilistic outcomes of measurements, and the ceaseless fluctuations of fields and energies. Through this lens, the uncertainty principle emerges not as a barrier to understanding, but as a gateway to a deeper appreciation of the intricate and restless nature of reality. The universe is vast, mysterious, and yet surprisingly suited for life. This observation has led scientists and thinkers to explore a fascinating concept called the Anthropic Principle. It essentially proposes that the universe's physical laws and constants appear fine-tuned because if they were not, life and conscious observers like us could not exist to notice them. Imagine a universe where gravity was too strong or where atoms couldn't form. In such a universe, stars and planets would never emerge and life would be impossible. So why does everything seem so perfectly balanced? The Anthropic Principle offers a compelling explanation. It shifts the focus from questioning why the universe allows life to acknowledging that we exist because the universe is just right. This idea has sparked debate and reflection. Some see it as a mere observation, while others view it as a profound insight into the nature of existence. The principle doesn't imply that the universe was designed for us, but rather that we are the product of the universe's particular conditions. Now, this naturally leads to a question. If the universe seems fine-tuned, does that mean there is a designer? This is where things get interesting. The argument for design without a designer comes into play. Think about biological evolution. Complex life forms didn't arise from a preordained plan, but through natural selection and random mutations. Similarly, some argue that the universe's conditions may not need a designer, but could be the result of underlying principles that naturally allow for life-friendly environments. In physics, randomness and natural laws often work hand in hand. The idea of a designer is appealing because it offers a simple explanation for complexity, but it also raises the question, who designed the designer? If we attribute the universe's fine-tuning to a higher intelligence, we're left with the challenge of explaining that intelligence's origin. This line of thinking can lead to an infinite regress, which is why many scientists prefer explanations grounded in natural laws. Instead of invoking a designer, physicists like Leonard Susskind suggest that the concept of the landscape can support anthropic reasoning. The landscape is a term used to describe the range of possible physical laws and constants that could exist. According to theories like string theory, the universe might not have a single, fixed set of laws. Instead, there could be a vast number of possible configurations. In this context, the Anthropic Principle becomes a way of understanding why our universe is the way it is. Among the many possibilities, only certain configurations would allow life to emerge, and we happen to exist in one of them. This idea doesn't require a guiding hand. It's similar to how evolution explains the diversity of life without needing a creator. The landscape is filled with different possibilities, and our universe is just one where the conditions happen to support life. It's not that the universe was designed for us. Rather, we find ourselves in a universe that permits our existence because it's one of the few where life can thrive. The Anthropic Principle also challenges us to think about the philosophical implications of existence. If life is a rare and special outcome of natural processes, what does that say about our place in the cosmos? Some find this perspective humbling, as it emphasizes the fragility and uniqueness of life. Others feel it diminishes the need for a grand cosmic purpose. The universe doesn't need a reason for being life-friendly, it simply is. Philosophers have long pondered questions of purpose and meaning. The Anthropic Principle suggests that meaning may not be inherent in the universe, but is something we bring to it. Our existence doesn't necessarily imply a grand design. Instead, it highlights the remarkable interplay of chance and necessity. The universe is complex and dynamic, governed by laws that allow for stability and change. Life emerged as a result of these conditions, not as a predetermined outcome. This perspective also touches on the nature of scientific inquiry. Science seeks to explain phenomena through natural laws and empirical evidence. The Anthropic Principle aligns with this approach by offering a framework for understanding why the universe is suitable for life without invoking supernatural explanations. It encourages us to explore the limits of knowledge and to appreciate the beauty of a universe that can give rise to conscious beings capable of pondering its mysteries. In contemplating the Anthropic Principle, we're reminded of the power of observation and reflection. The universe's fine-tuning might seem extraordinary, but it's precisely because we exist that we can recognize it. This isn't a coincidence, but a fundamental aspect of how we understand the world. It challenges us to think deeply about the nature of reality and our place within it. For centuries, scientists have been asking the same questions about the origins, composition, and future of our universe. Thanks to advancements in technology and groundbreaking experiments, we now have an unprecedented opportunity to peer into the farthest reaches of space and time, uncovering insights that were once beyond our grasp. Some of the most intriguing findings have come from the study of dark energy, cosmic inflation, vacuum energy, and the possibility of a multiverse. These discoveries are not just reshaping our understanding of the universe, they're providing evidence that challenges long-held assumptions and inviting new ways of thinking about the cosmos. What if the universe isn't as simple as we once thought? What if the things we can't see or understand play a much larger role in shaping reality than we imagined? These are the kinds of questions cosmologists are now answering. Let's start with dark energy, a mysterious force that's driving the accelerated expansion of the universe. Dark energy was first proposed after astronomers observed that distant supernovae were moving away from us faster than expected. In the late 20th century, scientists realized that the universe wasn't just expanding, but that this expansion was speeding up over time. At first, it was assumed that gravity, the force that pulls objects together, should slow the expansion, but the opposite was happening. In the late 1990s, two independent teams of astronomers using different methods confirmed the presence of a mysterious force that seemed to counteract gravity and accelerate the universe's expansion. This was dark energy, a force that makes up about 70% of the universe's total energy content. But how do we study something that we can't directly observe? The answer lies in studying its effects. Supernova studies were key in making this discovery. When a Type Ia supernova, an exploding star, was observed in distant galaxies, it became clear that these explosions were occurring at a much faster rate than expected. By measuring the light emitted from these supernovae, scientists could determine how far away the galaxies were and how quickly they were moving. The observations showed that the universe was expanding at an increasing rate, which pointed directly to the presence of dark energy. But there's more. Scientists also look at the cosmic microwave background. CMB, the faint glow left over from the Big Bang, which provides a snapshot of the universe when it was only a few 100,000 years old. By analyzing the CMB, scientists can measure the distribution of matter and energy across the universe, further confirming the existence of dark energy. The CMB gives us a look at the conditions of the early universe, and when combined with supernova studies, it paints a picture of a universe dominated by dark energy, pushing galaxies farther apart every moment. As we look deeper into the universe, we encounter another crucial piece of the cosmological puzzle: cosmic inflation. Cosmic inflation is a theory that suggests the universe underwent a rapid expansion during the first moments after the Big Bang. This brief but powerful growth would have stretched the fabric of space-time, smoothing out any irregularities and setting the stage for the universe we observe today. The idea of inflation was proposed in the 1970s by physicist Alan Guth. According to the theory, the universe expanded faster than the speed of light for a fraction of a second, growing by an enormous factor. This rapid inflation explains many of the features we see in the universe, such as the uniformity of the cosmic microwave background. Without inflation, the universe would have been much more uneven, with large-scale structures like galaxies and clusters of galaxies not able to form in the same way. What's fascinating about this theory is that it doesn't just explain the current state of the universe, it also provides insight into the very mechanisms that shaped it. Inflation provides a framework for understanding why the universe is so vast and structured the way it is. The theory has been supported by observations of the CMB, which show a uniform temperature across vast regions of the sky. This would be difficult to explain without the theory of inflation, which suggests that regions of space that appear far apart today were once in close contact before inflation stretched them apart. As we continue to study the universe, scientists are refining our understanding of inflation. Some believe that inflation could have lasted longer than previously thought, possibly leading to the creation of multiple, separate pocket universes, each with its own unique properties. While the full details of inflation remain a subject of ongoing research, it is clear that it played a pivotal role in shaping the universe. Now, let's dive into the concept of vacuum energy, another key element of cosmological research. Vacuum energy is a form of energy that exists even in the vacuum of space, where no matter or radiation is present. It arises from quantum fluctuations, which are temporary changes in energy that occur even in empty space. These fluctuations are a direct consequence of the uncertainty principle, a fundamental concept in quantum mechanics that states that the exact position and momentum of particles cannot be precisely determined at the same time. These fluctuations give rise to particles popping in and out of existence, creating a form of energy that fills space. While vacuum energy might sound like an abstract concept, its effects are anything but theoretical. In fact, vacuum energy is thought to be related to dark energy. Some scientists believe that the vacuum energy of space could account for the accelerated expansion of the universe. As the universe expands, the amount of vacuum energy increases, potentially contributing to the repulsive force driving the acceleration. The connection between vacuum energy and dark energy is still a subject of research, but it's clear that understanding vacuum energy is crucial for understanding the fundamental forces at play in the universe. Looking toward the future, one of the most exciting areas of cosmological research involves the development of new telescopes and experiments designed to probe the multiverse hypothesis. The multiverse is a theoretical concept suggesting that our universe might be just one of many, each with its own set of physical laws. While the idea of a multiverse is still highly speculative, advances in technology and cosmology are bringing us closer to testing this hypothesis. Future telescopes, like the James Webb Space Telescope, are expected to provide more detailed observations of distant galaxies, stars, and exoplanets, giving us a deeper understanding of the universe's origins and structure. These telescopes will not only help us explore the farthest reaches of space, but also study the very conditions that may have led to the formation of our universe. If the multiverse hypothesis holds any weight, it might be possible to detect signs of other universes, such as through patterns in the cosmic microwave background, or by identifying anomalies in the laws of physics that could suggest the influence of other universes. While this is still a long way from becoming reality, the potential for new discoveries is immense. As experiments and telescopes continue to evolve, we may soon be able to answer some of the most profound questions about the nature of the universe and our place within it. In conclusion, the field of cosmology is evolving rapidly, with groundbreaking discoveries offering new insights into the nature of the universe. The evidence for dark energy revealed through supernova studies and the cosmic microwave background suggests that a mysterious force is driving the accelerated expansion of the cosmos. Meanwhile, the theory of cosmic inflation provides a framework for understanding the universe's early moments and explains many of the features we observe today. Advances in the study of vacuum energy offer further clues into the forces shaping the universe, and future telescopes and experiments may help us test the intriguing idea of the multiverse. As we continue to push the boundaries of our knowledge, one thing is clear: the universe is far more complex than we ever imagined, and the discoveries we make will continue to challenge and expand our understanding of the cosmos. The debate surrounding the Anthropic Principle stands as one of the most contentious and thought-provoking issues in contemporary physics and cosmology. Some scientists argue that the fine-tuning observed in the universe's physical constants cannot be coincidental and must have some deeper explanation. They believe the Anthropic Principle offers insight by suggesting that the universe's laws are precisely calibrated to allow for the existence of life and conscious observers. On the surface, this seems reasonable. However, critics of the Anthropic Principle contend that it borders on tautology, merely affirming that the universe must allow for life because we are here to observe it. This criticism touches on the fundamental nature of scientific inquiry, whether a concept like the Anthropic Principle provides genuine explanatory power, or whether it is simply a philosophical reflection masquerading as science. The multiverse theory often intertwines with discussions about the Anthropic Principle, offering a potential framework to explain the apparent fine-tuning of the universe. Proponents of the multiverse theory suggest that if there are countless universes, each governed by its own physical laws, it is unsurprising that at least one universe, ours, would have conditions suitable for life. While this idea is intellectually stimulating, it raises a critical question: is the multiverse theory falsifiable? A theory's falsifiability is a cornerstone of scientific validity. Critics argue that because other universes are, by definition, beyond observational reach, the multiverse theory cannot be tested and thus falls outside the realm of empirical science. Supporters, however, point to potential indirect evidence, such as patterns in the cosmic microwave background or implications derived from string theory, as ways to substantiate the multiverse hypothesis. This tension between the empirical and the theoretical highlights an ongoing philosophical debate about the boundaries of science itself. The relationship between science and metaphysics becomes especially significant when exploring such abstract concepts. The scientific method relies on observation, experiment, and falsifiability to build reliable knowledge. Metaphysics, on the other hand, deals with questions of existence, necessity, and ultimate causes, often beyond the reach of direct empirical inquiry. The discussion of multiverses and fine-tuning inevitably blurs these lines. When scientists explore the conditions that make the universe hospitable to life, they touch on questions that have traditionally been the domain of metaphysics or even theology. Does this integration enrich scientific inquiry, or does it dilute its rigor? Can metaphysical perspectives offer meaningful insights into questions about the universe's origins and structure, or do they risk overstepping into speculative territory? These questions underline the complex interplay between empirical evidence and abstract reasoning. The study of fine-tuning and multiverses also brings ethical considerations into sharp focus. The allocation of vast resources to investigate theories like string theory or the multiverse, which may not yield direct experimental confirmation, raises important questions about scientific priorities. Should the scientific community focus its efforts on potentially untestable theories, or should it prioritize areas with more immediate practical applications? Beyond the practical, there is also an ethical dimension related to the implications of these theories. For instance, presenting the universe as one of many, with our existence as a statistical inevitability, could challenge deeply held religious or philosophical beliefs about purpose and design. Researchers must navigate these implications carefully, balancing the pursuit of knowledge with sensitivity to its broader impacts. The scientific community's debate over the Anthropic Principle is rooted in its potential to challenge long-held assumptions about the universe. The principle suggests that the universe's conditions are not arbitrary, but are instead finely tuned to allow for life. For some, this idea is a stepping stone to deeper understanding, while for others, it appears to be a dead end, a philosophical statement rather than a scientific hypothesis. Critics argue that the principle lacks predictive power, making it untestable and thus unscientific by traditional standards. Proponents counter that the principle provides a framework for understanding why the universe's laws and constants take the values they do, even if its utility is more conceptual than empirical. This disagreement reflects broader tensions within science, where the quest for understanding often pushes the boundaries of what can be experimentally verified. In the context of the multiverse, the Anthropic Principle takes on new dimensions. If there are infinitely many universes, each with different physical laws, the principle could simply reflect our position in a universe where conditions happen to allow for life. This perspective transforms the apparent fine-tuning of our universe from an extraordinary coincidence into a statistical inevitability. However, the multiverse theory itself remains contentious. Its detractors argue that it strays into metaphysical speculation, offering an explanation that cannot be empirically tested. Supporters, however, maintain that the multiverse is a natural extension of existing theories like eternal inflation and string theory. They argue that even if direct observation is impossible, the multiverse's implications can still be explored through indirect evidence and theoretical consistency. The philosophical implications of the Anthropic Principle and the multiverse extend beyond science, touching on questions of existence and purpose. If the universe is one of many, with no particular significance assigned to its specific properties, what does that mean for our understanding of reality? This perspective challenges anthropocentric views, suggesting that our existence is not the result of deliberate design, but rather a consequence of statistical chance. Such ideas can be both liberating and unsettling, prompting reflection on humanity's place in the cosmos. At the same time, they raise questions about the role of science in addressing existential and philosophical concerns. The relationship between science and metaphysics is particularly evident in the study of fine-tuning. When physicists explore why the universe has the properties it does, they engage with questions that have traditionally been considered metaphysical. For instance, what determines the values of fundamental constants? Why does the universe exist in its current form rather than some other? These questions straddle the boundary between science and philosophy, highlighting the need for interdisciplinary dialogue. Some scientists are wary of venturing into metaphysical territory, concerned that it may undermine the empirical rigor of their work. Others embrace this intersection, arguing that addressing fundamental questions about existence requires an openness to philosophical inquiry. Ethical considerations are also central to discussions about multiverse and fine-tuning research. The significant resources devoted to exploring these speculative theories prompt questions about their societal value. Critics argue that science should focus on addressing practical challenges, such as climate change or medical advancements, rather than pursuing abstract and potentially untestable ideas. Proponents counter that the pursuit of fundamental knowledge is a core aspect of scientific inquiry, and that breakthroughs in theoretical physics often lead to unexpected practical applications. The ethical implications of these debates extend beyond resource allocation. The theories themselves challenge conventional worldviews, raising questions about how scientific discoveries should be communicated and interpreted. Should scientists consider the philosophical and cultural impacts of their work, or should they focus solely on advancing knowledge? This tension underscores the broader societal role of science and its relationship with other fields of inquiry. As the debate over the Anthropic Principle, the multiverse, and fine-tuning continues, it reflects broader challenges in modern science. These discussions push the boundaries of empirical inquiry, blending scientific reasoning with philosophical reflection. They also highlight the need for interdisciplinary approaches, recognizing that questions about the universe's origins and structure often transcend traditional disciplinary boundaries. Whether through exploring the theoretical underpinnings of the multiverse, examining the philosophical implications of fine-tuning, or addressing the ethical dimensions of research priorities, these debates underscore the complexity and richness of scientific inquiry. In navigating these challenges, scientists and philosophers alike contribute to a deeper understanding of the universe and our place within it. The cosmological constant is one of the most fascinating concepts in modern physics, and it has a history that is as intriguing as its implications for our understanding of the universe. Imagine a force so subtle and yet so pervasive that it determines the fate of galaxies and the universe itself. This force, represented mathematically by the cosmological constant, originated in Einstein's equations of general relativity. Initially, Einstein introduced the cosmological constant to describe a static universe. At the time, this seemed necessary because the universe was thought to be unchanging, neither expanding nor contracting. The constant acted as a counterbalance to gravity, preventing the universe from collapsing in on itself. However, in the early 20th century, Edwin Hubble's observations of distant galaxies revealed that the universe was not static but expanding. This discovery rendered the cosmological constant seemingly obsolete, and Einstein reportedly referred to its introduction as his greatest blunder. Yet, as is often the case in science, what was once discarded would later return with even greater significance. The story of the cosmological constant took a dramatic turn in the late 20th century. By studying distant supernovae, astronomers discovered that the universe's expansion was not merely continuing, but accelerating. This acceleration was unexpected and counterintuitive. Gravity, which pulls objects together, was presumed to slow the expansion of the universe over time. So what could be causing this acceleration? The answer seemed to lie in a mysterious force known as dark energy, which makes up roughly 70% of the total energy density of the universe. And here, the cosmological constant made its return. In Einstein's equations, the cosmological constant could represent this dark energy, providing the simplest mathematical framework to account for the observed accelerated expansion. However, this reintroduction of the cosmological constant brought with it a profound mystery. According to quantum field theory, empty space, or what we might call the vacuum, is not empty at all. It is a seething field of energy with virtual particles constantly appearing and disappearing. These quantum fluctuations contribute to what is known as vacuum energy, and when calculated theoretically, this vacuum energy is staggeringly large, 120 orders of magnitude greater than the observed value of the cosmological constant. This discrepancy, often called the vacuum catastrophe, is one of the most significant unsolved problems in theoretical physics. Why does the observed vacuum energy appear to be so incredibly small compared to theoretical predictions? This question is not merely academic. It has profound implications for the universe we observe. If the vacuum energy, represented by the cosmological constant, were even slightly larger than its current value, the accelerated expansion of the universe would have been so rapid that galaxies, stars, and planets could never have formed. On the other hand, if it were smaller, the universe might have collapsed back on itself before life had a chance to emerge. The fact that the cosmological constant falls within such an extraordinarily narrow range has led scientists to describe it as one of the most finely tuned parameters in physics. This fine-tuning raises a profound question. Why does the universe seem so perfectly calibrated to support the existence of complex structures and life? One potential explanation for this fine-tuning is the Anthropic Principle, a concept that has sparked significant debate among scientists. The Anthropic Principle suggests that the physical constants of the universe, including the cosmological constant, take on values that allow for the existence of observers like us. In a vast multiverse, where different regions might have different physical constants, it is not surprising that we find ourselves in a region where the conditions are just right for life. This explanation shifts the focus from deterministic laws to statistical likelihoods, suggesting that the universe's fine-tuning is a natural consequence of our existence as observers. However, the Anthropic Principle is controversial. While some view it as a practical way to address fine-tuning, others argue that it lacks the predictive power of traditional scientific explanations and borders on philosophical speculation. The cosmological constant also highlights the deep connections between quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles and fields at the smallest scales, while general relativity describes the structure and dynamics of spacetime at the largest scales. The cosmological constant linked to vacuum energy bridges these two realms. It represents the influence of quantum fluctuations on the curvature of spacetime, demonstrating how the smallest scales of reality can have a profound impact on the largest. Yet this connection also exposes the limitations of our current theories. The vast discrepancy between the theoretical predictions of vacuum energy and the observed value of the cosmological constant indicates that our understanding of these fundamental forces is incomplete. Another aspect of this puzzle is the role of cosmic acceleration in shaping the universe's fate. The accelerated expansion caused by dark energy ensures that galaxies are moving farther apart over time. This has significant implications for the long-term evolution of the universe. In a distant future, the accelerated expansion could lead to a scenario where galaxies become so far apart that they are no longer visible from one another. This isolation would mark a profoundly different universe from the one we observe today, where the cosmos appears interconnected on grand scales. Some theories even suggest that if dark energy's influence grows stronger over time, it could lead to a big rip where the expansion becomes so extreme that it tears apart galaxies, stars, and even atoms. The cosmological constant is thus not just a number in an equation, it is a determinant of the universe's ultimate destiny. The apparent fine-tuning of the cosmological constant has also prompted new approaches in theoretical physics, particularly in the context of string theory. String theory, which seeks to unify all the fundamental forces of nature, predicts a vast landscape of possible physical laws and constants. In this landscape, the cosmological constant could vary across different regions, corresponding to different pocket universes within a larger multiverse. In some of these universes, the cosmological constant might be too large or too small to allow for the formation of galaxies and stars. Only in the rare regions where the constant falls within the narrow range required for complex structures would life have a chance to emerge. This idea, while intriguing, presents its own challenges. Testing the existence of a multiverse and the variations in physical constants it implies remains beyond the reach of current observational capabilities. As we delve deeper into the mysteries of the cosmological constant, it becomes clear that this single parameter encapsulates some of the most profound questions in physics. It is a window into the interplay between quantum mechanics and relativity, a key to understanding the universe's expansion and fate, and a challenge to our traditional notions of fine-tuning and natural laws. The cosmological constant is not just a relic of Einstein's equations, but a central player in the ongoing quest to unravel the nature of the cosmos. As scientists continue to explore these questions, they are not only probing the limits of our understanding, but also opening new avenues for discovery, reminding us that the universe, in all its complexity, still holds many secrets waiting to be uncovered. The future of understanding the universe is one of the most exciting and challenging frontiers in science. We are living in a time where questions about the very fabric of reality are not just philosophical musings, but scientific endeavors supported by cutting-edge research and technology. From the vastness of the cosmos to the tiniest quantum particles, scientists are exploring realms that were once beyond the reach of human comprehension. But what lies ahead? How will the next breakthroughs shape our understanding of existence? These questions are at the heart of modern physics, cosmology, and quantum mechanics. As we develop new technologies and refine old theories, we are inching closer to answers that could redefine our place in the universe. One of the most thrilling aspects of the future is how technology and science are converging to address the biggest questions. Advanced tools like the James Webb Space Telescope are transforming the way we observe the universe, capturing light from the earliest galaxies and probing phenomena like dark energy and vacuum energy. This telescope is more than just a tool for seeing distant stars. It is a window into the past, revealing how the universe evolved over billions of years. AI is playing a critical role in this exploration, helping researchers analyze massive datasets from telescopes, particle accelerators, and other experiments. Machine learning algorithms can identify patterns and anomalies that would take humans decades to uncover. Imagine an AI discovering a hidden law of nature or detecting a subtle shift in cosmic patterns that leads to a groundbreaking theory. Could the next major leap in understanding come not from a human mind, but from a machine's ability to process data at unimaginable speeds? This technological revolution is not limited to telescopes and AI. Quantum sensors, which measure gravitational fields with incredible precision, are unlocking new possibilities for understanding the interplay between gravity and quantum mechanics. These sensors could one day help detect the elusive effects of vacuum energy, or even provide the missing link between general relativity and quantum theory. Similarly, quantum computers are emerging as powerful tools for simulating complex quantum systems. These machines can model the behavior of particles in energetic environments, shedding light on phenomena that are otherwise impossible to study directly. This combination of precision sensors and computational power could be the key to resolving some of the most persistent mysteries in physics. At the heart of these mysteries is the question of vacuum energy. According to quantum field theory, empty space is far from empty. It is a seething cauldron of fluctuating energy, with virtual particles constantly appearing and disappearing. This vacuum energy is thought to play a critical role in the universe's accelerated expansion, yet its exact nature remains poorly understood. Theoretical calculations of vacuum energy yield values that are staggeringly large, many orders of magnitude greater than what we observe. This discrepancy, often referred to as the vacuum catastrophe, highlights the limitations of our current understanding and points to the need for new theories or insights. Could future technologies or experiments finally unravel the secrets of vacuum energy, bridging the gap between quantum mechanics and cosmology? The implications of solving these mysteries extend far beyond physics. Understanding vacuum energy and its role in the universe's expansion has profound philosophical and existential implications. If vacuum energy is indeed responsible for the accelerated expansion, it also shapes the ultimate fate of the cosmos. Will the universe continue to expand forever, growing colder and darker until it becomes a lifeless void? Or could there be a scenario where this expansion reverses or transitions into something new? These questions force us to confront our assumptions about time, space, and existence itself. They also challenge us to think about our place in a universe that is governed by forces far beyond our control. In string theory, the landscape represents a vast array of possible universes, each with its own physical laws and constants. Our universe, with its precise conditions that allow for life, may be just one pocket in this multiverse. This idea challenges the traditional view of physics as a search for a single, elegant theory that explains everything. Instead, it suggests a probabilistic framework where the conditions we observe are simply one set of possibilities among many. While the concept of a multiverse is controversial and difficult to test experimentally, it opens new avenues for thinking about fine-tuning and the apparent coincidences in our universe's laws. What if the precise value of vacuum energy is not a cosmic accident, but a natural outcome of living in a particular pocket of the multiverse? This shift in perspective has profound implications for how we approach the search for meaning in the universe. For centuries, scientists have sought to uncover universal truths, laws that apply everywhere and always. The idea of a multiverse challenges this notion, suggesting that the laws of physics might vary from one universe to another. This raises difficult questions. Are we special because our universe allows for life, or are we simply one instance in an infinite array of possibilities? If the multiverse exists, does it diminish the significance of our existence, or does it make it even more extraordinary? These questions are not just scientific, they are deeply philosophical, touching on themes of purpose, identity, and the nature of reality. As we move forward, the interplay between theory and observation will be critical. Theoretical advances in fields like string theory and loop quantum gravity are providing new frameworks for understanding the universe, but these ideas must be tested against empirical evidence. Observations from telescopes, particle accelerators, and other experiments will either validate or challenge these theories, pushing science forward. This dynamic relationship between theory and observation is the engine of progress, driving us closer to answers about the nature of reality. The future of understanding is not just about solving equations or verifying theories. It is about expanding our capacity to ask better questions. As our tools and technologies improve, so too does our ability to explore the unknown. The questions we ask today about vacuum energy, the multiverse, and the fate of the universe are rooted in a desire to understand the fundamental nature of existence. They reflect a uniquely human curiosity, a drive to make sense of the cosmos. As we gaze into the vastness of the cosmos and dive into the depths of quantum reality, one thing becomes clear: the universe is not just a place we inhabit, but a mystery we are unraveling piece by piece. The questions we've explored about vacuum energy, the multiverse, and the ultimate fate of the universe are not just puzzles for scientists. They're invitations for all of us to wonder, to imagine, and to dream. What lies beyond our current understanding? What discoveries await as we push the boundaries of knowledge with ever-advancing tools and theories? Perhaps the greatest mystery is not what we have yet to uncover, but how each answer transforms the way we see ourselves and our place in this immense, intricate universe. So stay curious, stay questioning, and remember, our journey into the unknown has only just begun.